Okay, so today is mostly PCA, and I was initially basing it on a notebook by a previous postdoc who worked with Claire, and apparently she presented some notions of dimensionality reduction for a challenge on some hurricane prediction data. And I just added this small notebook PCA basics, where we're going to start from, and just give you intuition what's happening. I'm sure you have already seen it in the part of the class in the slides, but when you code it, it's much more clear, so we're going to start with that, okay? Okay, so here I'm just creating some 2D data, okay? And then I'm multiplying by a matrix. It's 3301. It means that the second dimension is just going to be the same dimension the same features generated by the normal distribution, but the first dimension now is just a linear combination of the first two coordinates, okay? So just taking like 3x1 plus 3x2. So if we plot it here, the data just gets kind of expanded following the first diagonal, okay? So the role of PCA is to find the direction that will so it's like to find a line on which, if we project the data, is going to have the maximal projection, okay? So what happens here is that, let's imagine we have a vector u. In this case, we can imagine it's the first diagonal, okay? Then we project the data or the samples that we have on that line, and we sum the square of the projections, okay? This is also called the variance explained by the by the unit vector u, okay? So we want to find the line that will explain the maximum information, or have a maximal explainability following that vector, okay? So in 2D, it's very nice it's very easy to model this vector. It's a unit vector, then we can just parameterize it using angle theta, okay? We know that if we take the Euclidean norms, so just cosine square plus sine square, it's just going to be 1, okay? So if you remember your physics class, that's basically the polar coordinates, okay? And finding this vector u is equivalent to finding the angle theta that will explain the majority of the projections, okay? So here I'm just going to return, first question, just easy here. We're just given the angle theta, return u, so it's just going to be MP array. There are multiple ways to do it, but I'm just going to do it the simple way. Okay. And now I want to compute this sum that I computed there using the samples in the matrix X and then the unit vector u, okay? So what happens here, I can loop through the samples or the rows of X, but I can also simply do X at u, okay? So this will give us the scalar product between the samples in X and the unit vector. Now I can just do the square, okay? So now I'm getting the scalar product squared, and finally I just take the sum. Okay. All right. So now what we're going to do is basically doing some kind of a grid search, or just a binning Okay, we are mostly interested in the range from 0 to the angle pi. Okay, we're doing a discretization, so the step here is 1/200. And for each of these angles, we're going to compute the projection sum using that angle. Okay, and finally, we're going to try to find the best theta that gives us basically the maximal projection sum. Okay. There you go. Yep. Something is off. Okay, perfect. There you go. All right. So here I don't print the theta, I print theta over pi. So it's like 0.25, okay? So it means that the angle in this case is pi over 4, which means just the first diagonal, approximately, okay? So it makes sense because we see that the samples are spread following the first diagonal. So if we project on the first diagonal, we're going to get maximum sum of projections, okay? There is another way to explain PCA, which is I want to project the samples in a way that the linear reconstruction of the data will be the best one, okay? So what happens here is that I'm taking the line, okay? I'm projecting the data on this line, and then I'm taking the difference. You can look at this as the residuals from the projection. So if I subtract the projection, I want this to be minimal, okay? You can call it construction loss. So I want to project the data linearly so that the projection, it minimizes the reconstruction loss, okay? And you can prove that maximizing the first quantity that we showed is the same thing as minimizing this quantity, okay? And we're going to see. So the construction loss is a bit tricky. You can loop, of course, but we don't want to do that. So I'm going to take x. I'm going to subtract the projection. Projection, we already done it, okay? Now, this is basically a 1D array, but here I want for each row in X to subtract the reconstruction. So to do it without doing loops, I just have to make sure the dimensions are correct. So in this case, it's gonna, this element here is going to have 200 elements, okay? And then if I multiply by u, this element here is going to have 2, okay? So the trick here, I'm just going to add some dimensions to make sure that the product makes sense, okay? So here it's 200, this is 2, so I'm just going to do 200 by 1 multiplied by 1 by 2. Okay, so this formula gives me the difference. Now I just have to sum, or I can just use NP linear norm. I don't have to do everything myself. So I do linear norm. I want to compute the norm for each of these rows. This is basically 200 by 2. So I'm going to do axis equal 1. So I'm computing the norm column-wise. So in the end, I'm going to have 200 elements. Now I just take the square and then finally the sum. Is it clear or need to break it down more? Okay. So x multiplied by, this is 200 by 2. This is 2. So this is going to be 200. Okay? And this element here contains the scalar products, xi. Okay. Now I want for each of these coefficients to multiply it by u. Okay. By u here is shape 2. Okay. So if I do u none, this now has shape 2. This now has shape 1, 2. Okay. And then when I do 2 dots none, then this one is going to have 201. Yeah, so I just do, again, matrix multiplication, 200 by 1, 1 by 2 is going to be 202. Okay? Sometimes if you just try to get the right shape, the formula is going to be good. All right, so we're doing the same thing here, but this time we're trying to minimize. Instead of taking the argmax as previously, we're just going to take the argmin. There you go. And you see that it's the same best data I get. Okay. Theoretically, you would say, well, it has to be 0.25, but our data is random, and then we're not exploring the entire space. We're just taking a discrete version of the angles. Okay. So plot direction here, just gonna plot the data and the line directed by the angle that we have found. Well, now we learned basically the first principal component, okay? If we want to learn the second principal component, we can do it iteratively, okay? So what happens here is that we take the sample, we subtract the projection that we got following the first principal component, and that will be our new data. Now we try to do the same thing on this on these new samples, and that way we'll be getting the second principal component. In this case, it's 2D. We know that principal components form a basis of the data space. So if we already have the principal component, then we know its basis. It means that the second principal component has to be orthonormal to the first one. So you don't have to do fancy things to find the second one. But generally, imagine we are in like 10 dimensions, and you only want the first 3 principal components, then you have to go through the computations, okay? So here I'm just subtracting the projection following the first principal component, and this is the new data, okay? And here it's very easy to find the second principal component, since the samples are all on the same line, so all the variance or all the projections are going to be explained following the second diagonal, okay? So just visually, we know that the second principal component is just going to be the other diagonal, okay? I'm sure you have seen in the class that there's a much easier way to do it. You just take the eigenvectors of the covariance matrix of this data set, all right? So the way you do it in NumPy, first you compute the matrix C, and then you have to find the eigenvectors and the eigenvalues. We know that C is symmetric, okay? So that's why we use H, I think eigen-Hermitian, something like that. It helps and it makes calculations much more accurate, okay? If you don't specify that it's symmetric, you might get some floating error problems and the numbers might be complex values, okay? So if you know that matrix C is symmetric, it's good to use eig-H instead of eig. So eigs here are going to be the eigenvalues, and vects are going to be the eigenvectors, okay? So here I'm just plotting, I took the eigendecomposition of of matrix C, okay? Then I'm getting the eigenvectors and then the eigenvalues, then the eigenvectors. One thing you'll notice here is that the first eigenvector is going to be, Okay. So, if you look at the eigenvalues, what does it look like? Remember here that the eigenvectors are the columns of vectors. They're not the rows, okay? So these are the columns. The second column is associated with the highest eigenvalue. So H will give you these in increase in order of eigenvalues. So the first eigenvalue is going to be the smallest one, and the first eigenvector associated with it will be the first column of vectors. The second eigenvalue is going to be the second eigenvector, or it's the second column. But here the value that we get in here is exactly what we have saw initially. So here we computed the sum of the projections, okay? So let me just go to proj, and I'm just going to try to print the maximum. There you go. So the quantity that we maximized is exactly the eigenvalue associated with it, okay? So the projection, or basically the objective value associated with the first principal component is the eigenvalue associated with that eigenvector, okay? And you can check if you want that once we do the substitution and we take x2, which is the residual after we take the projection following the first principal component, if you compute the projection for that case, you're going to get 59, okay? And these quantities is what we call the variance explained by the principal components, okay? So the first component will explain around 1,795 variance, and the second component is going to explain less. And it makes sense since we said the first principal component is going to explain more than the second one, and the second one is going to explain more than the third one. So expect that these quantities has to be in decreasing order. Okay? So this is, in a nutshell, the logic behind PCA. Find the direction that will explain maximum variance. Once you do that, go again, find the second one, the third one, until you reach a certain threshold. Usually, we will, if for example, if we have like 100 features, you can either say, okay, I'm going to stop at 40, 45, or 50, or you can say, I'm going to stop at a level where these projections are equal to around like 90% or 95% of the norm of our original samples. So we're going to look at that in the second notebook. Yeah, so this is credited to Sophie. I don't know exactly what the features are, but you're getting some wind speed, and then you're getting some historical path, acceleration, velocity, and all of that, and you want to predict at future instances. It's a very similar problem to what we're trying to do in the challenge of homework 6, but in this case you have all the features in one data set. Okay, so this is also a warm-up to get you familiar with Panda data frames, because you're going to use them for homework 6 a lot. There are many ways to do things in Panda data frames, but it's good to do it the way you're supposed to. I see a lot of people using loops. That's not the reason Panda frame was used. If you use loops on Panda data frames, it's much slower than using loops on NumPy. So let's see. So here I'm just gonna load the data. So it's read CSV. I like to use this path class. It makes things much easier. For example, I can just do data p divided by train.csv, and this is basically like join path. Okay. So let me just comment these to show you what's happening here. There, this is my data set, okay? So the target, or basically the labels in this case, are wind speed. I just want to get rid of some features that are not relevant to the problem. So in this case, I can do yTrain. This is the target value. It's going to be df, and I'll just do target. And for xTrain, it's going to be df, but I'm going to drop these columns that I don't need here, okay? So the way you do it is that you can do drop there you go. So I got rid of the target and the other values. There's usually when you're working with large data set, you probably want to do things in place. So what's happening here is that I'm taking a copy of data frame, df. I'm dropping the columns from this copy, and then I'm saving it in xTrain. Okay? So imagine I do this. Instead of xTrain, I do this. So in the intermediate step, I'm basically I have to create two copies of df. The original one, and then the one without the columns, and then I replace df, okay? So before this assignment is performed, I end up with two copies of df in the memory. So usually when you have a large data set, you don't want to do that, so you can just do drop, and then you can say in place equal true, okay? So in this case, the columns are going to be dropped from the original data frame, and we're not going to create a copy, which is much faster. But here, that's not a problem, so I can just stay with my original formula. Oops. All right. Okay, so now I'm going to do this data. It's going to be the same thing. I just have to do here. I'm just going to do test instead of train. And here TS. Okay. It's a good practice to standardize the data. I think in PCA you can choose whether you want to do that or not before you reduce the dimensions. But usually there is at least centering. Okay. Standard scalar, we used it before, so I'm sure you're familiar how to use it. We just keep in mind that we fit the standard scalar using the training data, not the test data. And now, since we already have seen in the toy example how PCA works, we're just going to use it from documentation. I need documentation. We're going to need it. Okay. So here I'm just fitting using the features. There's this argument SVD solver. So this is for the eigen decomposition problem. Is it a full one, or is it what do you call it? What are the possible values for SVD solver? Yeah. So it's just basically what's the backend that you are going to use, and whether it's full or not. These are just approximations. sometimes the matrix is too large and you're not interested in all the eigenvectors, so you can specify different arguments just to say, okay, I'm not interested in an accurate answer. I just want something that's approximately correct. Okay. All right. So now, when you feed the data, you get an attribute called explained variance. Okay. And explained variance is exactly what we had initially, which is the eigenvalues. Okay. Let's look at this. Let's do some tests. I have my X train. What I'm going to do is I'm going to do np linog.norm. All right. And now, since explained variance is basically the eigenvalues, I'm just going to test whether this is accurate or not. And I'm just going to sum everything. I think I need a square somewhere, but let's see. I think we need a square. Yeah, these are large one. Okay. So before we saw that the eigenvalues were sorted in increasing order. In this case, it's decreasing order. We put the first principal component, then the second one, then the third one. Okay. What was it? Let's see, I think x is equal 1. And then we're taking the sum. Now we're getting too much. No, it doesn't match. Yeah, I have to check this later. Okay. So what's happening here is I'm going through the explained variance values. Okay. I'm taking cumulative sum. So in the first position, it's just going to be the first PCA. The second position is going to be the sum of the first of the two first explained variances. The third position is the third, and vice versa. Okay. And the threshold, I want to stop where. Okay, so here it says max, but it's actually the last one because we know that explained variance is greater than 0, so it's always going to be increasing. Okay, so what happens here is just I'm going to count. I'm going to go through the cumulative sum of explained variance. I'm going to stop once I get to 95% of the total explained variance. Okay, so when I do that. So I'll just basically go through cumulative sum. Once I go beyond the threshold, I stop. Why? Oh, sorry. It was. Come on. All right. There you go. So from over the 370 features, if I use there are 22 dimensions that I need to get 95% of the full variance. Let's look at 99%. Okay. So around 62 dimensions contain 99% of all the variance that I have in the data. Okay. It doesn't mean that the other ones, yes?
Oh, is the explained variance kind of like the R-squared value?
Explained variance. But R-squared, we're working with labels as well. You're looking at the residuals.
Right.
But we have no residuals here. We're not using Y-train at all.
Right. We just have unlabeled.
What's that?
This is unlabeled.
What's that?
Is this like, we don't have like a label data?
We're not using the label there. We're going to look later how the projections match with the labels, but so far we haven't used the labels. Yeah. So the explained variance should be the squared of the eigenvalues, if I'm not mistaken. Okay. So that's basically the sum of the square of the eigenvalues. Those are, that's basically explained variance. And what do we get? Yeah. So that's basically the projections that we have seen before. It's the sum of the scalar products. You can go to slides to find, I don't remember, is it eigenvalues or eigenvalues squared, but it should be either one of those. Okay, I'm just going to stay with 95. It's nice. All right. So here I'm just plotting the threshold, which is the 95% of the total variance. And here, this is the cumulative sum of the of the explained variance. So around 22, I'll reach 95% of the total variance. It doesn't mean that the remaining 5% is irrelevant, because it might be relevant to the labels. We haven't used the labels yet, okay? But this is unsupervised learning. We're not allowed to do that, okay? So we just hope that the principal components that we got so far are going to do relatively well on the prediction. All right. So here I'm just going to do the same thing, but now I'm using a second argument called n components, okay? And in this case, I'm telling PCA, when I call transform, I don't want the entire principal components. I only need the first 22 components. All right, now we're going to get some colors. There you go. So what's happening here is I'm plotting the first component versus the second one. And then I'm using as a coloring, I'm using the labels. Yeah, I think this method here, transpose taking 0, is kind of redundant. You don't need all of that one. Right. Okay. So the way we have used PCA is the same way we're going to use many of the other dimensionality reduction methods from scikit-learn. Many of these are not going to be covered in the class, but you can always go and explore them. I especially recommend that you check what we call TSNE. It's outside the scope of the class, but if you're interested in something very powerful, TSNE is the way to go. TSNE is used in many visualization applications. You can use it in the challenge as well. And for example, You can use it on MNIST without even providing the labels. It provides a very clear clustering of the different numbers. Okay. So it's based on Kullback-Leibler divergence. I think I mentioned it before in office hours, but it's basically an information-based matrix. Okay. But for us, here we can explore a much simpler one, which is called the isomap, or multi-dimensional scaling. So what's happening here is that we are going to learn lower dimensional representation of the data that will mimic what we call the geodesic distance. So what is geodesic distance? Imagine I have a sample here, x1. I have another one, x2, and I have another one, x3. Okay? So the distance between x1, x3, let's say is 3. Here it's 1, and here it's 1. So what is the geodesic distance between x3 and x1? So in this case, the geodesic distance is 2. So geodesic distance is basically what is the shortest path, the distance between like x3 and x1. What is the length of the shortest path between two samples, okay? And in this dimensionality reduction, I want to map x1 to z1 and x3 to z3 so that the geodesic distance between x1 and x3 is the Euclidean distance between z1 and z3. It's magic, okay? So I want the shortest path in my original space. I want to learn a lower dimensional space where the Euclidean distance mimics the shortest path distance in my original data, okay? So you can imagine, for example, in Gaussian mixture models, when I have those clusters, in that case, I want to map them to a Euclidean space where if the samples belong to the same cluster, they're going to be very close, okay? So we have seen, for example, if you have two clusters, okay, these points here are very close, but we're not interested in those. So basically, you want this to go somewhere here, or basically you can map this one to one line and the other one to another line, something like that. So even though they look close in the original space, but when it comes to shorter distance, they are much closer to other samples that might visually look like they are distanced. So you twist in the space. It's no longer a linear relationship like PCA. In PCA, it's mostly a linear projection, but in this case, it's no longer the same. Okay? And the problem with this method is that you will have to compute the pairwise distances. Okay? So if you have in data, that's C2 out of n, which is around n squared. So if you have 1,000 samples, you might end up with 1,000,000. So what happens there is that you say, I'm not going to compute the distance between each sample and the entire data set. Sorry. So between each point and the other one, so that's going to be, yeah, n squared. Okay. So what happens here is that you're saying, I'm not going to compute the distance between each sample and all other samples. I'm just going to compute between each sample and like two neighbors. Okay? So in this case, we're just going to reduce the number of samples we have in X-training so that we can run the samples. When you do that, you're going to get a sparse matrix where each row will constitute the distance between sample, like first row is going to be the distance between sample 1 and the rest of samples. But since I'm using a smaller number of neighbors, the matrix is going to be sparse, okay? So if you run it normally, you're going to get some warnings. I just hate those, so I put this import here to reduce the warnings I get. Because they're going to tell you there's a much efficient way to do it, but that's not our issue here. Yeah. So here we're just going to compare the two methods, the MDS and the multidimensional scaling and the isomap. And we're going to display those. They should take a little bit more time than PCA, but that's normal. Come on, you can do it. Okay, I think I have so many things happening in my laptop now. Okay, so while it's running, there are other methods that incorporate supervised and unsupervised learning. If you remember in random forest, we have done a dimensionality reduction method. Do you remember it? So we created random orthonormal matrices from the, if you remember, the QR decomposition. So that was a dimensionality reduction method. It's random in a way that you don't know you're not trying to maximize or minimize anything. But from a probability perspective, you can also show that if you use, if the data has a higher dimension and you use, for example, you drop from 1,000 features to 100 features, you can show that in expectations, you can get a good approximation of your data. Oops, this is not defined. Okay. There you go. Yes, definitely a weird shape, but it's kind of expected because we're trying to mimic a shortest path. Trying to mimic a shortest path distance, which is the geodesic distance. So the space is going to be twisted sometimes in a violent way. Okay. And don't rely on plots to evaluate the performance of your clustering. Okay. Some people say, well, it's yellow. Yeah, but I mean, you can have a yellow on top of a blue one. So it's good to have some other measures to look at the dimensionality reduction. Usually, you just train a classifier on the reduced dimensions and see how it performs compared to the full dimensions. That's basically usually your best guess. Yeah, this one was presented in the conference, and it's outside the scope of the class. But the idea here is that you can combine supervised and unsupervised at the same time. Okay, so here you're doing the prediction and the dimensionality reduction at the same time. This is based on a Bayesian learning method. If you have heard it before, basically you're assuming distribution, usually a Gaussian distribution over the parameters of the linear classifier. And then you can put some constraints on that distribution. For example, you can say, well, I can imagine it's a Gaussian, but then the covariance matrix is diagonal. It means that the weights of the coefficients are independent, something like that. Okay? And using Bayesian learning, you can also add some constraint that will give you results similar to the lasso solutions. If you remember, it's lasso, a lot of coefficients going to 0. So that's basically a feature selection method that's happening there. Okay? So here, just going to fit let me fit this one. I see how fast it goes. Oops. Yeah, it's going to take some time, but let me just do. So Gaussian random projection, we're already seeing something very similar. Spectral embedding is basically a more general framework for SVD or a PCA. It can also include the spectral clustering as well. Johnson-Lindenstrauss is a more general term for the random matrices, like the orthogonal matrix that we have seen for the random forest. You don't have to worry about those, but these are basically hints or things, tricks that you can use for homework 6. If you end up creating too many features, you can use one of these methods to reduce the dimension and save yourself some training time. Okay. So with this kind of classifier here, we can see the values of the weights. So you can see that we have a wide range of features that have 0 coefficients. So those are basically ignored. All right. The highest weight is something around 180. So this is basically feature selection. We're going to call it also dimensionality reduction. And in this case, you're just ignoring a certain set of values. Let's look at how many of them are non-zero. I'm not sure all, let's see. Yeah, none of them are exactly 0, but many of them have very small norm. So you can just basically ignore them in that case. Oops. Any questions? Yeah, you don't have to submit anything for this assignment. For this lab. You can go home and enjoy your break. Any questions related to homework 6? No? Okay. Yep, that's pretty much it. Thank you for your attention and happy holiday.